I will speak about this this kind of problem for a four-order equation. This is a joint problem, a joint paper that I did with Professor Jebari, who is a research from Tunisia, right? Mm-hmm. And okay, so we will consider existence and multiplicity of solutions, right? But more specifically, we are considering four-order equation with integral perturbation on the conditions, right? The idea I thought is similar and can be applied to another kind of problems, right? I will center more my questions in the properties of the linear part, right? And finally, I will show some, okay, the result for nonlinear ones, but I will not, explain just the techniques, because are more technical. So I prefer to give more in the part of the green function, because I think that this is more applicable to other similar, different but similar problems, because the ideas could be similar, right? For the nonlinear equation, nonlinear part, okay, so the green function is for the first, and the nonlinear problems, the existence is deduced from Krasnodębski fixed point of by the Leggett-Williams fixed points. Okay, I will show some examples. Right, this is the paper that it is compiled. These results that I will talk about, right, with Professor Jebari. And okay, first to say that when we are speaking about the four-order equations, general, this is useful in general because usually, right, they characterize the deformations of an elastic beam, are very well known in the study of the bridge, for instance, right, in the stationary models, right. They are given usually for a four-order equation. Of course, the simpler case, the stationary equation that goes from a PDE to a ODE, right? And the boundary conditions models the different ways to get the bridge, to get the beam, right? Depending of it is clamped beam or other kind of situations, and that study the deformation of the beam. The constant sign of the solution is very important because, okay, so if we have a beam, right, which is, okay, depending on the form to get it, right? But when we have here some force, right, this force, the weight is in this direction, so it is expected, sorry, it is expected that the deformation has in this direction, okay, have the same direction that the force, the external force. No? It is not obvious that this happens because you can get something like that, but we can get something here. If the force is just in one side, yeah, of course, you have it here, but maybe in the other side of the bridge, of the beam, you can have some kind of oscillation, and this will have a problem because you can get the oscillation of this structure, and okay, this structure can fall down. No? So the idea is that it's important just to have that the solution that we have is the constant sign, is just in the line of, in the direction of the external force, right? Okay, to get this kind of problems, there are many ones that has been studied. Use it, okay, degree theory, shooting method, fixed points, critical point, lower and upper solutions, or other kinds, for instance. Here, in this paper, for instance, I show only a few ones, right? This paper, it is used the lower and upper solution method. For instance, Davis and Henderson uses the shooting method here to deduce existence of solutions. In this one, by they use the Leray-Schauder-Debré methods combined with ring functions. In this paper that I did with Professor Thies and Professor Sanchez from Lisbon, okay, we use lower-and-upper solution related with spectral theory with a different kind of boundary conditions. For instance, Bonanno here use critical point theory because of, okay, the weight solutions, okay, and it deduce existence of solutions in this direction. And in this one graph, it is used the Leray-Schauder-Debré combined with the properties of the ring function of homogeneous boundary conditions. Okay, there is only a few examples of different kind of arguments or different kind of tools that are used to avoid this kind of problems, but there are, of course, many works in this direction. So first, I will work on this problem, right? If we consider a simpler one, right? It is dependent of mu, right? U4 plus mu, right? And we consider these boundary conditions, 3 points here, 3 consecutive zeros at 0, and 1 0 at 1, okay? This four-order equation for any function, continuous function sigma, of course, it may be in L1, right? So we are looking for one solution with this idea, no? 3 times on the left, 1 time on the right, and we are looking for u constant sign, positive or negative, right? And more consistently, what we are is to, we want to ensure the uniqueness of solution, right? And show such solution like this, in this way, right? Where the kernel Gm is the green function. This, what we know is the green function. Of course, once we know the green function, it is the solution, it is directly what we must do is to integrate this times sigma. We move sigma, but the green function is inherent of the solution of the equation, depends obviously on the equation, but depends on the boundaries. Okay, so both of them give the kernel. If we move the equation or we move the boundary conditions, of course, the green function, the kernel moves, right? But once we have the kernel, for any sigma, the solution is even by them. In particular, okay, if the green function is positive and sigma is positive, u will be positive, for instance, this kind of things, right? And of course, we can have any other properties or a priori bounds, etc., right? Okay, so let me remember what we understand by a green function. Remember that we have a function which is defined in a square, m times r, is continuous, and it's continuous in this case just the first and the second derivative, right? So we have a C2 function, and when we have with the third and fourth derivatives, right? In this case, the continuity is just in the triangles, right? We have our square, and we have the continuity here, but not happens in the diagonal, right? So these are the 3 properties of the regularity. And remember that we may characterize it because when we fix S and consider as a function of t, it satisfies the homogeneous equation, right? For t different from S, right? The second one, condition here, is what happens in the diagonal, right? We have that there are not continuity, and the diagonal is this one. Okay, the third derivative, we have it paced, but paced with jump equals to 1, right? This is, okay. what we have in this case, it was the first derivative, we have S, we are moving in T, and when we have here, we have a jump in this situation, right? So we have the regularity here, and we paste in this direction, right? And finally, it satisfies the boundary conditions, right? So it vanishes 0, first and second derivative, and it vanishes a 1, right? So there are the 6 definitions of the Green function, and one can show that if we have a unique solution, it satisfies if there exists a unique Green function, and it is characterized by 6 properties. So the graph may be something like that, okay? Remember that it will be a solution of the equation, and 3 zeros here, 1 0 here, and it, okay, has some singularity here. Of course, this is G, we cannot appreciate, but if we represent, for instance, the second derivative, remember that we have here the 0, have G, first derivative, second derivative, not here, because the second derivative is not 0 here, and we have a jump, something like that, for any S0, right? So we are moving in T, and this is more or less the shape of the Green function, right? And so for this case, when we are with these boundary conditions, right, in this paper with Fernandez Gomez, a former student, first we prove that this is just the spectral condition, okay? Our problem has a solution if and only if this condition 2 does not hold, okay? When tangent is not hyperbolic tangent, right? And in this case, say does not hold, right? We have a unique solution, and this unique solution is given as a Green function. In this paper, okay, we obtained the exact expression. This is the problem of the Green function in general, okay, is that to calculate the expression is when the coefficients are not constant, it's almost impossible to get the expression, right? And when the coefficients are constant, we have here with other college, Thith, one of the former students, we have developed an algorithm that we are able to calculate the expression, right? We can put, this is a free software, okay, but it is in Mathematica. One needs to Mathematica, but if you like, I can send you the page, the web page. It is free to use, okay, but it is necessary Mathematica program, right? And so you only must to put the coefficients constant, to put the boundary conditions, and so you get the expression. The problem is that the expression many times is very complicated, and so it is complicated to manage it, right? Of course, one can plot it, even depending on a parameter. In the program, you can put parameters, not necessarily exact values, right? Okay, so one can plot and can see what is the movement of the behavior of the Green function, but it is difficult in general to get a exact proof of the values, right? Which are the optimal values on the parameters where the Green function is positive or negative, right? So I have done anyway that in general, the Green function, if it has constant sign, not for this in general, right? For any boundary condition, if it is positive or if it is negative, the Green function will decrease on the parameter n, right? Okay, if we have in general, not for this, right? But if we have a general equation, ln of u, an order equation, plus mu, parameter m, right? And we have plus boundary conditions. Okay? So if this problem has a unique solution, right? And the green function has constant sign. What we have is the following. If we move in M, right, this is a general result, right? What we see is if it is negative, it will be decreasing in M, right? And it breaks, right, just in the first eigenvalue, okay? And on the right, or maybe it changes sign, or it is positive. And in this case, it will be decreasing on M2, right? The optimal value here, okay, so it finalizes or start just in the eigenvalue. Moreover, it finalizes here or here, and these values, okay, it may be plus or minus infinite, but it finalizes here in a real value. This is never eigenvalue. Okay, it is a regular point. So if you are interested in calculate this optimal value, right, M bar, M tilde, these are never eigenvalues, right? This is an eigenvalue. This is the main eigenvalue. This is very easy to calculate the main eigenvalue. Okay, you only must to work the Bronsquian, that is trivial, right? But the difficulty here is when you are trying to calculate it analytically, okay? Of course, numerically, you plot the green function, you may get some estimates, right? And so here, in this problem, in this paper, remember when I have with Carlos Fernandez, we study just the values of M, and we characterize the values where the green function of the problem 3.1 is strictly negative. To do this, we study the disconjugacy theory. Okay, it is a very well-known the Buto-Koppel, and here, using this theory, we characterize just the values where M, the green function, is strictly negative. It can be for these values on M, you see, M1, 4, open. This will be the first eigenvalue, because the first eigenvalue is always for any kind of problem. And we characterize this one, right? And so, in fact, what we have at this is M1, remember, this is just the eigenvalue, tangent equal hyperbolic tangent. And we deduce, in that case, we study the expression of the green function, and we verify that just here, look that this is a closed interval because it is never an eigenvalue of the considered problem, right? It is given by this expression. Okay, this to 4, right? And that time we obtained it by studying the green function, but we are not able to relate it with anything. Okay, so this we study the problem. Okay, this is the optimal value, right? But after, with another student, Lorena Saavedra, right, we consider a general Km minus K problem that included this one as a particular, right? The Km minus K means K zeros in one side and M minus K zeros in the other side, right? And at least one of these, at least 1 0 at 0 and 1 0 at 1, at least one, right? It is not considered the initial and the final problems because, of course, they have not taken values, right? And so with these conditions, we prove there that in general, okay, the green function will be, if n minus k, right, is odd, it will be positive and never negative, right? And if n minus k is odd, it will be negative and never positive. And when it is positive or negative, it finalizes just in the eigenvalue, of k m minus k, because this is a standard, right? And the other one is just to move one here to here, right? Or here is the minimum of putting k zeros here, 1 plus and minus 1, or minus 1 here and plus 1 here, okay? And so there, in this result, we characterize the value of the constant sign green functions in a spectral way, right? But what happens? Here, we know that this is an eigenvalue of our problem, k I minus k, right? We know, sorry, that this never is an eigenvalue of the problem k I minus k, but it is an eigenvalue of problem, imagine, k minus 1, m minus k plus 1, right? This may be, okay? And the question is that it is an eigenvalue of a different problem. But to calculate eigenvalues is a very simpler way, numerically. Of course, to get it analytically is complicated, but numerically is trivial. We have problem. We have a mathematical package which you can do it for any kind of equations. You don't need it constant coefficients. And so we can get the optimal values, obtain the optimal values, without calculating green function. Because the calculus is very complicated, and in general, it is impossible if the coefficients are not constant, right? And so we characterize this kind of, and we have any other kind of conditions that we characterize too. But in particular, for our case, the problem M14, right, remember, is the eigenvalue. And I remember this is general. It is always the first eigenvalue. But the other one will be, remember, k minus k is 2, right? So we go from the first eigenvalue of the problem 2, 2 zeros, to the first eigenvalue of 3, 1, right? And it is characterized, because it is a general result, without calculating the green function, okay? And to get the expression, the set expression is, okay, it's really very easy in this case, analytically, and in general, numerically, it's obvious. It's a very trivial problem to calculate the eigenvalue, at least the first eigenvalue of any operator, right? Yes, moreover, we prove that, remember that 2 is the spectral conditions, and so we have solution when 2 does not hold, right? So the green function satisfies these other properties for our case, right? For our case, it satisfies when we fix t, right? It satisfies the solution, the homogeneous solution for S different from t. Fix t, move S, right? In my paper with Saavedra, what we prove is that when we are derivating respect to S, this equation, fixing t and moving S, it is, the green function solves the adjoint equation. What happens is that in this case, the adjoint equation, okay, but the boundary conditions are not the same. And what happens when we are deriving respect to S is that the zeros, the 3 zeros, sorry, goes to 1, and 1 0 goes to 0, right? So we are working with the problem 3, 1. When we fix X and move t, the green function is 3, 1. But when we fix t and move S, our problem is 1, 3, right? This is a particular case of the general one because it is the adjoint equation, right? And this is a general condition. general property. With independence if the green function has constant sign or change sign, right? What happens when it has constant sign? When we are in the values minus m0 plus m1. In this case, okay, we have the derivative is negative at 0, the third, because the 0, 1, and 2 is 0. So the first one is negative, and the first one at u1 is positive, right? So this is very simple, but this is restricted to the case for the green function negative, right? And when we are with S, okay, we have the similar one, but in this case, the first, and here 3, right? But these properties are when it is negative. This is not a general property. This is a general property. This is a property valid only when we have constant sign. And so, what we have in our situation? In our situation, what we consider is the problem, right? With a value m. We have here plus f. Remember that at the beginning we are equals to sigma. When we have plus f here, it will be equals to minus sigma. And so, okay, my green function will be minus in this case. It changes. We consider the problem 3. And here we are interested in what happens when at u we consider a boundary condition like this. Okay, this to say that it is a very general, if instead of to have the integral condition with Lebesgue-Riemann integral condition, we put, for instance, the Stieltjes integral. Because if we put here a Stieltjes integral, right, it covers any possibility, linear possibility at least, of the conditions that we can put here. Multipoint, integral in AB, integral with PS, US, any kind of things will be covered in this derivation, right? It may be the arguments are similar, but I use this because, okay, in this case we are able to get some exact values. In the other case, we need to get some estimations, but it is possible to work in this more general framework, right? So our interest in this case is what happens with M and what happens with lambda. Sorry, I think some chat. Okay, so because I have this. Okay, so the idea is to get lambda to get M. No? And so we are thinking about for which values of lambda M we can ensure that the green function is positive or is negative. What happens, right? This will be the idea at the beginning. Because I am interested in the constant sign, and then at the end to apply this constant sign to deduce existence results for the nonlinear problems, right? My idea is to go to work with fixed point theorems, with Leray-Schauder, with this kind of arguments. Of course, this is, if one thinks in critical point theory, this is not the way, but when we are speaking for fixed point, this is, in my opinion, the best way to consider fixed point theory, right? So, we consider this problem. We will assume.
Sorry, Professor Alberto.
Sorry.
F. Alberto.
Okay, it's continuous. It may be Calateodori. Okay, we could speak in L1, okay, in a more general setting, but my idea here is not just this. I prefer to go about the shape of the function as we will see. But the function is non-negative. And we are in the values when lambda is, this condition, remember, means GM negative. Okay, so we are under this assumption, right? Answer. Okay, what I say that the problem 4 will be more realistic if we have integral 0,1 PS US ds, right? With P will be some weight, Okay, this can be done. Okay, but I explain this because we have the right values, right? Okay, because of this, it depends on P. We must put which class of one. But in this case, if we put P, right, we may have weight. P may be 0 in some parts. Okay, and it means that the displacement of U1, right, depends on the value of the function U, or in some parts of the whole B, right? Yeah. So the function will be non-negative when it is bigger or equal, and we say positive when it's positive in 0, 1. Of course, the solution by definition will be 0 at 0 and 1. So, okay, when we speak about positive, means positive in the interior, right? So what I say is that when we are speaking about the nonlinear problem, the solutions will be as the fixed points of this operator. Okay, this is the idea. And what I say is, okay, if we are able to obtain capital G, we have here all the conditions, or we may get it, all the properties of the linear problem, right? Which is the expression, which is the sign, which is the a priori bounds, etc., etc., right? And so, imagine if this is less than some constant k, automatically this will be makes k integral f SUS, something like that, okay? So we can get some a priori estimates. Okay, the expression that we did is this. Now I put the expression, but we prove we obtain the values, the exact values of lambda, for which the capital G is positive. Remember, it's positive because we move f on the left side. Okay, we are not speaking equals to f, we are speaking equals to minus f. Okay, and we have here a problem. Okay, a problem. We are assuming that we are here, right? Sorry, this is the situation. What we will be to characterize what happens here, right? When m is between the values for which the ring function is gm, not capital, is negative. But we don't know what happens here. Okay, here, okay, when lambda equals to 0, here we know that it changes. We know this, right? But it may be, it is expected that there are some part here in which gm remain positive. Yeah, but this part we are not able to work. And we have not characterized this. Okay? What we say is
problem knows again. Some happens.
It deals with internet connection.
I think internet connection again. Alberto,
excuse me.
internet connection.
Okay, no,
Yeah,
okay.
sure.
I don't know what happens that it disappears. Sorry.
Okay, okay.
What say is that here gm changes. Okay,
Yeah,
on
yeah.
this side. Okay, but this side is open. We don't know what happens here, right? Okay, so this is what we have. And how we deduce this? We deduce this because of the following property. When we have this one, remember we have the 3 zeros, and we consider here 1, right? It's not an eigenvalue. The eigenvalue will be 0 here. We have the existence of solution. There is a unique solution if and only if we are not on the eigenvalue. Okay, this is a very simple problem, right? So we have a solution if and only if we have not in an eigenvalue. This unique solution, well, we will name W, and we can prove that for m less than m14, it is positive. Okay, sorry, it is positive in 0, 1, open here. And remember, m14 is the first eigenvalue. So on the left, on the first eigenvalue, the unique solution is always positive, right? We can verify this. And moreover, when we consider the same problem, but instead of 3, 1, problem 1, 3, right? I have said before, this is the adjoint. It means that we have the same eigenvalues and we have this other property, that the green function related to this problem is just the green function related to the other one, but with ST. When it is self-adjoint, it is symmetric, but this is not self-adjoint. But anyway, this is a generic property, right? And taking into account this, we can define this function, set, as the integral of G star. And it is obvious that set is just the solution equals to 1, because will be the integral of the green function times 1, coupled with the conditions 1, 3. Okay, so it is very simple. And okay, studying this property, this expression, one can say that it is negative. Okay, it is negative. Okay, it is negative here. It's very important, right? Here. And we have that, remember that we have set 0, the first derivative will be negative, the third derivative, okay, so the third derivative positive at 1, and the first is negative at 0. Okay, this is a technical question that I will use now, okay, because to get the construction of the cone, okay. So these properties I am using to construct the cone, okay. And so with these technical properties, we prove that this problem, this is the general problem, sorry, has a unique solution. This, okay, Cn is just the integral of Wn. Okay, so we obtain the spectrum of the integral problem as a function of the spectrum of the non-homogeneous, of the homogeneous problem of lambda equals to 0. This is the problem, right? And we can prove, express the expression of G capital, capital G, as a function of the homogeneous problem. This is the green function, remember, when lambda equals to 0. We have here again the green function. This is the spectral condition where it appears Wn, okay? And so from on the right, okay, from the homogeneous problem, we deduce the expression of the non-homogeneous problem. This is a general property, and now I have recently published a paper in which I have a general one, right? For any conditions, we can put one problem as a function of the other one. Knowing the green function of one, you can obtain the green function of the other one, right? This is a general one. When we did it, this we didn't know, but recently in a paper in mathematics, in collaboration with two students, we have proven that this property is general one, right? For any kind of boundary conditions. Okay, the expression is more complicated, of course, but this is a generic property, okay? If you consider problem 1 and problem 2, if you know the solution of problem 1, you can deduce what is the solution of problem 2. Explicitly, okay? You can do it. I can send you the paper of the reference if you like, but it is okay? It is an expression in this sense, right? Okay, I'm sorry because I am too much time. Okay, so first, when we are here, we prove that GM is positive, the first one. This is very simple because for these values, GM is negative, so minus is positive. This will be negative, okay? This is positive, this is negative, everything is positive. So, which is possible, it's trivial, don't worry. And the important thing is this order. Because this kind of properties is fundamental to introduce, to define a cone and to apply degree theory, Krasnodębski, Williams, etc., 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 right? In general, what we need is that the Green function, in general, right, must be less than, imagine, right, phi1t, set of S, phi2t. We need something like that, okay? If we consider some proof, some property in this direction, we are able to define a cone, right? But we need the same here. This is important. And this is what we have. Look at this. We have set. Remember the set S has defined it in advance as the integral of the adjoint problem, right? And here we have HT, we have a constant here, right? Okay. And so, forgot the left, but this function that I put here is just 1 over Cm. Cm is the integral of that, right? So we are working here in this part, right? The first one, as I told you, is trivial, that is positive is immediately. And the other one is given like this, okay? We consider GMTS over G1S. This has a singularity of S equals to 0 and S equals to 1 because this function will be 0. We are dividing 0 over 0, right? And so this is a continuous function except here, S0, S1, because there we have 0 over 0. What happens? We study the limit when S goes to 0, and okay, because of the properties set, applying L'Hopital 1, 2, 3 times, right? Taking into account the properties of set, etc., this kind of technical properties, we prove that this is positive, and the same when S goes to 1 minus, okay? This is because of the construction of set, W, etc., etc. And this is fundamental for us in this argument that this function is negative, that the derivatives on 0, 1 are positive, negative, okay? So, since we have this is the situation. For any S, for any T, sorry, we have that the solution is positive, but when S goes to 1 is positive, when S goes to 0 is positive, so we may extend it in the whole I times I. So we can get the singularities are just a positive value. So we have a positive function in a compact set, have a minimum, which is positive, and so by definition is 0, right? And of course, since it is continuous, it has a maximum. And so we deduce the expression. Remember that future is just the expression that we like. Okay, so this is the solution, and my function, remember that I put set s here, in practical, in our situation, is G1S, okay? That appears at my set MS, right? So with these properties, we may check the following one. If we need positive, because H0 is 0, if we put delta in 0, 1, okay, we have 1, we have 0, and we put delta here. So we know that for any delta, we can get some gamma, for which H is positive in delta 1. And so we can put here delta. Okay, and so we can get, but okay, for any S, but for any T in delta 1, we may deduce this. This is very simple. Of course, this is less than the other side, right? And so this is important, we can, because we have that this is positive, and so we can define the cone in this direction. And so to finalize, right, this is the way that we can define, for instance, the cone. The cone may be defined in several possibilities, but this may be. This is one possibility. There are more, of course. Depends on delta gamma. Delta is arbitrary. For any delta, we have the gamma, right? Bigger or equal, and we have that the minimum in delta 1 is bigger than gamma, this gamma, and R. Remember that R appears in the previous inequality, and it is related to the maximum, right? This is the cone, right? That we put K gamma delta. And so, for nonlinear problems, so I give it more quickly. The idea is this one, a fixed problem, and we put down one, the Krasnoselski, for instance. What we say, because F is continuous and bigger or equals to 0, which is the condition H0, we can prove very simple that it is a completely continuous operator. This is very simple, right? And because of the properties of the Green function, right, with this gamma and R, right, we know that it applies the cone in itself, okay? And this is very important and very fundamental, this kind of properties, right? Because you have the integral of GTS, F, right? F is bigger or equal. And so you know that this is phi2, sorry, phi2 of t, it appears, integral set S, F, right? But at the end, this is phi2 of t, assuming positive, right? And C set S is bigger, right, than the maximum of GTS over phi1. Okay, so this is the idea. And at the end, what you have is something like that, phi2 of t, phi1 of t, and we have the norm of TU. Okay, so this is TU. So this is the idea, okay, roughly speaking. Then by using the property of the Green function, you can translate it to a cone. Here is, okay, phi1, phi2, assuming it is continuous. Of course, this is very quick. Of course, in any case, we must be careful about this, but roughly speaking, this is the idea. And so we have this property, and this is a property that we know we need, for instance, for Krasnoselski. And in general, we have a compact, a completely continuous operator in a cone in itself. Is what we need to apply Krasnoselski, Lefschetz, Williams, etc., and degree theory, etc., right? And so this is technical. Okay, I don't check anymore, but okay, so if we have all the time for this M, consider these values. Okay, it can see, okay, this is a technical one, but when we have delta 2, we can plot it, right? Expression of the normal set. Okay, there are technical matters, so it is not easy to translate, but are technical things. At the end, what we can say is that if we are able to get a set, a sequence of m values, maybe 1, maybe 2, maybe 3, for which delta 2 and delta 1 are the constants related that we have with the green function. If f satisfies these two properties, I give the graph now. It's bigger than and smaller than, depending on it. Something like that. Okay, so to get the idea, this may be the graph. What we need is for some value till rk, the function f is bounded from above. But in a part here is bounded from below. These kind of things. And this may be several times. Okay. What we do is that in any of these times, we can apply Krasnoselski. And we prove that norm tu less than norm u, norm tu is bigger than norm u. And so combining this, we are able to get this one. We have 2m minus 1 solutions that satisfy this. And this is a sequence of the Krasnoselski fixed point theorem. Okay? 1, if m is 1, we have one solution, and if not, we can get 3, 4, 5, etc., etc. Right? This is why so we define these omegas in the cone, and we apply several times. Because what we must use is that some parts has non-common points, okay? To be sure that the solutions that we had in one situation is not the solution that we had in the previous one, right? We must be careful with this, but it is a direct application. To deduce, for instance, using Lefschetz-Williams, we can use gamma 3, gamma 4. Notice that, for instance, gamma 4 is not valid if delta is 0, because the minimum is 0 here, because G0 S is 0, right? So in this case, we need for delta strictly positive. And in this case, under these conditions, let me show something like that. Again, some combination. I give an example on the graph. We can deduce this kind of at least two solutions. This is the classical one of the Lefschetz-Williams. In this case, this will be the shape, okay? Near to 0, it cannot be bigger than. In an intermediate interval, must be over something. And here, it is not bigger than this. Something like that, okay? And with this kind of shape, we can use Lefschetz-Williams theorem and deduce at least two solutions. We cannot ensure, okay, if 0 is not solution, we can ensure that there is at least 3, okay? But we can ensure 3, but we are not able to prove that 0 was not solution, right? Okay, so this is the idea. Some examples, for instance, when we have m equals to 0, in this case, remember that lambda, is 1 over cm, that in our case will be 4, in this case, right? And what we say is the degree function can be given directly. This is the expression. But here, notice that we have lambda. The function h depends on lambda 2. Look at this, right? But we may obtain it directly. Okay, so for a particular case, one can give the exact value of the green function, the exact value of h. And okay, so choosing this kind of values, one can prove for this case the existence of solutions that anyone are going to zero when k goes to infinity, right? And for instance, in the second case, if we consider a function like this, we could apply the second one, the Lecce-Williams, and we can ensure, right, that at least one is less than 1/30, that the minimum is bigger than 1 in 1/4/1, and similar with this, right? This kind of arguments. Okay, this is all. Thank you for your attention. If you have any questions.
Thank you. Thank you. Very nice talk. Now, about questions discussed, advice, please. Alberto, very nice talk.
Thank you.
Interest, but I would like to see careful, because I think for linear case also many my questions about my knowledge, because here very interesting non-local conditions, non-local. It is important, and there is many applications.
Yes.
And also other side, historically, I graduated Krasnoselsky department. And
okay.
his advisor Sobolevsky, my advisor Sobolevsky, like grandfather, native.
I didn't know. I met Krasnoselsky
I know.
many years ago in some conference, but of course, for
Sure,
me, it's,
I know very well.
You know,
and,
it's the greatest one. Right?
yes, this is very important for me.
Yes.
Your interest and your investigations, but my really my interest connected maybe linear